Okay, hi everybody. I'm going to take you through PAG 3.1. PAG 3.1, which is your chance to determine the entropy of neutralization, the enthalpy change of neutralization. So the technique you're going to use here is pretty straightforward. It's one that you've seen, that you are quite familiar with the basics of. Let's try again. Okay, everybody, I'm going to take you through PAG 3.1, which is the determination of the enthalpy change of neutralization. So what you're going to use is plastic beaker, polystyrene beaker, and a thermometer, and here I've got 25 centimetre cubes of some aqueous HCl and some aqueous NaOH. And we're going to mix them and study the temperature increase, and from that we can determine the enthalpy change of neutralization. So what we're going to do is use a technique called cooling curve extrapolation, which sounds complicated, but it's not really, and it's a very accurate way of determining a quick temperature change. So what you do is you put, I can't remember which one, it's either HCl or NaOH, you put one of them into your beaker first, and you measure the temperature of the solution to the nearest 0.5 degrees. So in this case that is 20.5. So at 0 minutes it's 20.5 degrees, and you're going to do that for the first 3 minutes, because sometimes you will find that your reagent has been kept in a cool stockroom or a warm stockroom, and you can find that actually it takes 3 minutes to reach the temperature of the lab. So we're going to take the temperature every minute for the first 3 minutes, and as I'm going to hurry this up, let's say it goes naught. Sorry, not naught. After 1 minute, it's 20.0. 2 minutes, it's 20.0. 3 minutes, it's 20.0. Okay, and so it's settled down to a constant temperature. Now, when the clock ticks on to 4 minutes, what you're going to do is instead of taking a measurement, you're simply going to add the other solution. So if this is HCl, you're going to add the NaOH, and you're going to simply stir it and allow the temperature to rise. Now, the reason we use this cooling curve technique is that when we add the reagent, the temperature of the water, which is the surroundings, the temperature of the solution, which is the surroundings, to which the energy is being supplied, it jumps up very quickly. But it takes time for that increase in temperature to be registered on the thermometer. The extra energy has got to be conducted through the glass of the thermometer. It's got to heat up the spirit inside, that's got to expand, and it takes quite a while. It can take too long essentially, and it means that by the time the spirit in the thermometer has reached a maximum, the solution has already cooled down a bit, and so you don't actually register the full temperature increase because it takes too long for the thermometer to actually register what's going on. So this technique allows for that. It allows you to calculate what we think the real rise was. So let's say this is 4 minutes, and I'm going to add my NaOH, and I'm going to stir. Okay, and I'm now simply going to wait until the time ticks on to 5 minutes. So for 4, I'm not going to take a measurement. For 5 minutes, and let's say this is the 5th minute, I'm going to take my temperature of the solution, and let's say for me the temperature is 28.0. Okay, and I'm going to keep stirring and take temperatures every minute. And of course, you can see that gradually the temperature is going to cool down. It's going to decrease as energy is lost from the water to the air of the laboratory. And so, yes, already I can see that's down to 27. Okay, and etc. You can imagine filling this out gradually. It would decrease and decrease. Etc. And you will keep recording some data until we've got sufficient. Now, what you do then is plot what's called a cooling curve, and I'll do that quickly so you can see what we're going to do. The y-axis is temperature, and the y-axis is time. We're going to use minutes. Okay. And you plot your data, so 0, 1, 2, 3, 4, 5, etc. Okay, and the temperature, it's going to be, well, let's say 0. Obviously, you'll have graph paper. Okay, so this is the temperature, this is the time. And you can see that at first, so from 0, 20.5, it's going to be about here. 1, it dropped down to 20, then stayed there. So we've got an initial curve like that, and then at 4, we didn't take one, okay? So at 4, at this point, it's supposed to be a straight line, at this point, okay, we did not take a reading. Then, at 5, we did, and it was up at 28. Then at 6, it was 27. And then, let's say it drops off like this, okay? So what we want to do is guess what temperature the solution jumped to at 4 minutes when we added the NaOH. Now, hopefully you can see that the way of doing that is to extrapolate back, to draw a line of best fit, okay? This isn't necessarily a straight line, this is a curve for me. I've drawn a straight line of best fit until it hits the vertical line from 4 minutes, okay? And I could fill this in for, okay, just for completeness. Okay, and so we think then the temperature jump at 4 minutes was from 20.0 degrees C2, and I'm going to need a bit more scale, to this point here, and let's say that was 32. Okay, and so we've got a temperature jump of 12 degrees, but the temperature jump we saw when taking the measurements was not 20 degrees, sorry, a jump of 12 degrees. A jump of 12 degrees, the jump that we saw here was only 8, look. But this has allowed us to extrapolate back and to guess what the jump would have been if we'd had a magic thermometer that could have instantly registered the temperature change, and that's called a cooling curve extrapolation. So this here is delta T. And from there you can use Q equals mc delta T. Q is the heat energy supplied to the aqueous solution, because the water is the surroundings. The system is the NaOH and the HCl. The water that they're dissolved in is the surroundings. Q equals mc delta T. So we know what delta T is. We will assume that the heat capacity of the solution, the specific heat capacity of the solution, is the same as for water, so 4.18. And m, that's going to be the mass of the solution. And for us, that is if we assume 25 centimeter cubes of each is going to add up to 50 grams, then we could use 50.0 grams. 50.0 grams as the mass of our surroundings, and that will allow us to calculate Q, and then delta H, we could say that enthalpy of neutralization equals negative Q divided by N, and N is the number of moles of water that we have formed through this neutralization reaction, and you can calculate that because you know the concentration and the volume that you've used of each of the reagents.